Hey guys, so in this video, I'm gonna go over how you can approach proportional scheduling. Now, this is only one way of doing proportional. There are many ways, but this is how I did it when I did the assignment, and so I'll just explain this one approach. If you're not sure to get started, this is a good video to watch. Okay, so first I'm gonna go through an example of what proportional scheduling means, and I'm going off of slide 16. It's not the same numbers, but if you want another example, you can look at slide 16 of the lecture on scheduling, 4 or 5, I think. Okay, so let's assume we have three processes, P1, P2, and P3. P1 asks for 1/4, P2 asks for 1/3, and P3 asks for 1/10. So in the assignment, we tell you that a process is asking for m/n, and that, for example, 1/2, 1 out of 2, is not the same as 2 out of 4. If you want to do a more advanced scheduler, you definitely can take advantage of that, and for example, 1 out of 2 would be less flexible than 2 out of 4. But I'm just going to reduce everything to its strictest form, because it's just an easier way to do it. So for this implementation, I'm just going to think about these ratios as decimals or percentages. So this is 25%, this is 33%, and this one is 10%. Okay, cool. So in the first quantum, we pick one at random, really, because we don't have any information yet. So let's just pick the first one. And when we pick it, I'll just darken the corner like that. Oh, right, and let's assume P1 starts at quantum 1, P2 starts at quantum 2, and P3 starts at quantum 4. So the little star means process started here, or was created, and the little corner thing means we schedule that process. Okay, so since P1 is the only one that's alive at quantum 1, we pick that one. And now it has been picked one time out of one quantum that it has existed, so its utilization is 100%, 1/1. Okay, so we move on to our second quantum, and we look, alright, P1 has a utilization of 100%, but P2, who was just born, hasn't run yet, so its utilization is 0%. 100% is way more than the 25% that P1 asked for, and 0% is way less than the 33% P2 asked for. Therefore, we pick P2. And that kind of makes sense. You want to let P2 go because it hasn't run. So now P2's utilization is 100% because of the one quantum it's existed. It has run that one quantum, but P1's utilization is 50% because out of two quantums that it's existed, it has only run once, right? So 1 out of 2, or 50%. Cool. So we move on to this third quantum. We're deciding between P1 and P2 because remember P3 is not born yet. P3 is born until quantum 4. So P1 has a utilization of 50%, and P2 has a utilization of 100%. P1 asks for 25%, and P2 asks for 33%. But 50% is less. There's a less of a distance between 50% and 25% than between 100% and 33%. So the most unfairly treated process is process 1. Because although it has received more than what it asked for, it has received more by a lesser amount than P2. So we pick process 1, and now it has run 2 out of 3 times, so its utilization is 66%, and process 2 has run once out of this 2 times, and so this is 50%. Okay, at quantum 4, we have 66% for process 1, 50% for process 2, 0% for process 3, because process 3 was just born here, And since 0% is way less than 10% that it asked for, we want to pick process 3 to run. Okay, so process 3 gets 100%. Process 1 has run 2 out of 1, 2, 3, 4 times, and so that's 50%. And process 2 has run once out of 3 times, and so that's 33%. Okay? By the way, for the midterm, you guys should be able to do something like this. Definitely practice filling out a table like this with all the utilization percentages. Okay, let's do one more. So at quantum 5, all 3 processes exist. Process 1 has 50% utilization, which is twice what it asked for, right? Process 2 has 33% utilization, which is exactly what it asked for, no more than that. And process 3 has 100% utilization, which is 10 times what it asked for. So the most unfairly treated is process 2, because it only got exactly what it asked for, not twice what it asked for like process 1, and not 10 times what it asked for like process 3. So even though it got exactly what it asked for, it's the most unfairly treated. And so that's the one we pick. And so process 2 has run 2 out of the 4 quantums it's been alive, so that's 50%. Process 1 has run 2 out of the 5 quantums it has existed, and so that's 40%. And process 3 has run 1 out of the 2 quantums it's existed, so that's 50%. Okay, so you guys get the idea of what we're doing here. And the key thing is that we are picking the most unfairly treated process, right? The one that either didn't get what it asked for, although we didn't really see that in this example, or the one that got what it asked for, but it didn't get as much more as the other ones. Like the other ones got way more than what they asked for, and the one that we pick is the one that got the least utilization ratio in general. And so the big idea is, what does this unfair mean? Well, we're going to associate this notion of unfairness with something called the compute ratio. And for this part, I'm looking at slide 17 of the same scheduling lecture. I can't remember. I think it's lecture 4. But it's the one that's titled scheduling. Okay. So what does this compute ratio mean? Compute ratio we're going to define as utilization over requested. So it's what I got over what I asked for. Right? And so there's basically 3 cases for the compute ratio. The first case is that the ratio equals 1. If the ratio equals 1, I've gotten, or the process has gotten, exactly what I asked for, right? Utilization equals requested, so what I have gotten, the utilization, the CPU I've actually utilized, is exactly the same as the CPU I've requested. Exactly what I asked. Okay. If the ratio is less than 1, this means that requested is bigger than utilization, right? The denominator is bigger. So that means that I've gotten less than what I asked for. What I requested is bigger than what I actually utilized, so what I utilized is less than what I requested. Okay? And the last case is that the ratio is, and I'm talking about the compute ratio here, is greater than 1. And so if the ratio is greater than 1, that means that utilization is bigger than requested. So I've gotten more than what I asked for. Okay, cool. And so basically, in this case, the first case, when I got exactly what I asked for, the process is pretty happy. When I got more than what I asked for, the process is even happier. But when I got less than what I asked for, the process isn't very happy, right? And so that's a problem. Cool. And so the big idea here that we're going to use for our algorithm is that the minimum compute ratio is the most unfairly treating process. This is the big idea. Okay? And that makes sense, right? Because the compute ratio is smaller. That means that relative to what I requested, my utilization is very small. And so the minimum compute ratio is the process that got the least utilization relative to what they asked for. Remember, this is all relative to what they asked for. If, for example, I have a process that has gotten, let's just do a quick example here. P1 requested and got. Requested 90% and it got 80%. And P2 requested 10% and it got 20%. We're not looking at what they got, right? Because P1 got way more than P2. We're looking at what they got in relationship to what they requested. P1 got less than what it requested. And P2 got more than what it requested. So we want to pick P1. And so that's why we look at this ratio. And so the minimum compute ratio gives the most unfairly treating process. Okay, cool. So what do we need to actually implement this? Well, since we've decided that we want to pick the process that has the minimum compute ratio, we're going to want to actually get the compute ratio for every process. And so compute ratio needs utilization and it needs requested. So how do we get, for example, requested? Well, requested for your assignment is just m over n, right? And this is given to you guys in my request CPU. Cool. So we have requested. That's good. What else do we need? Well, we got requested. Now we need utilization. Okay? And utilization, we are going to define as running time over a lifetime. And that's basically what we did in this example, right? So it's quantums I actually ran over quantums I've existed. Cool. And if we look at our table, that's exactly what we did. Like, how did I get this 50%? Well, I looked at running time, so I've run 2 quantums, right? Here and here for P2. And then alive time is 4 quantums, 1, 2, 3, 4. And so 2 over 4 gives me my 0.5 or my 50%. Alright, so we have a lovely formula for utilization, but this formula needs a running time and an alive time. So how do we get... Sorry, my OneNote's acting weird. Let's go down a little. Okay, how do we get the running time? Well, the running time is basically every time we schedule a process, we know that it has run for one more quantum. So we can just keep track of it and increment it whenever we schedule that process. Right? Because that means that it is chosen to run, and so it has run one more quantum. Alright, so what about this alive time? Well, the alive time, we want to increment every quantum that passes for every process that exists at that moment in time, right? This alive time is incremented every single quantum, regardless of whether or not we actually scheduled that process, regardless of whether or not it actually ran. So this one we want to increment. Whoa. Okay. Every quantum that passes. For all valid processes. Right, because if it's valid, that means that it exists. So, all existing processes. Cool. Okay, so, now we're getting a bit more implementation heavy. Let's think about what we need to know about every process. Well, we need to know what they requested, right? Okay. Or you can also store, so what they requested, remember, is m over n, and you could store that as a float, for example, or you could multiply it by 100 and store it by an int, if you like that better. You can also just store m and n separately, and just make the calculation m over n whenever you need it. Both are fine. Okay. Then we also need the running time. Right? How many quantums have they actually been scheduled to run? And we talked about how we might get that. We also want the alive time. Or how many quantums they have actually existed. Then, just like in any other algorithm you've done so far, you want to keep track of if that process is valid, and you want to keep track of its ID. Okay, and how do we store all these things? Well, you want to use something like a struct array. Okay, and if you're not quite sure how to do that, you can look at PA2 for an example. Okay. Oh, sorry, my OneNote is all weird. Okay. Cool. And you can find PA2 in my kernel too. Okay, and so that is basically the idea of how to get started on this. You can look at the second part of the video, which I'll upload at some point later today, about, and that goes into a little bit more details on, like, actually the methods and what those look like, and how this can become actual code.